Good day, doctor. My name is DNJ with matrix number 223604. Today I'll be presenting on the overview of first and second law of thermodynamics. So what is thermodynamics? Thermodynamics studies the flow of energy and its role in generating movement. It is rooted in the Greek terms therma, which means heat, and dynamics, which means power. The field connects heat energy to mechanical work and upholds the principle of energy conservation expressed in the first law of thermodynamics. The second law of thermodynamics emphasizes the energy quality, stating that natural processes occur in a direction and decreasing energy quality. So for its application in technology, it is integrated to contemporary technology, including electricity generation and the utilization of thermal energy. For its historical development, the history of thermodynamics is a foundation to modern chemistry and physics. It is progressed significantly in 1824 when Sadi Carnot demonstrated the heat transfer to produce work. Later, in 1850, William Rankine, Rudolf Clausius, and Lord Kelvin formalized the first and second laws of thermodynamics, solidifying the discipline. So let's take a look at the first law of thermodynamics. The first law of thermodynamics says that energy cannot be created or destroyed, only transferred between forms. So energy can be transferred as heat or work in a closed system. Energy can also be transferred through mass flow in an open system. So what we need to know that conservation. The total energy in a closed system is remain constant at all times. So in thermodynamic analysis, there is two types of energy, the macroscopic form and its microscopic form. For macroscopic energy, we have kinetic energy and also potential energy. For microscopic energy, we have internal energy, which is the translational energy, rotational and vibrational energy, and also the sensible energy. So energy can be transferred across a closed system boundary in two ways, heat or work. So what is heat? Heat is energy transfer due to temperature difference, and work is energy transfer through force and displacement. For energy balance equation, we can look at the bottom. Energy balance principle is derived from first law of thermodynamics, which is the energy in minus energy out equal to the change in energy system. So a change in energy system equals to final energy minus initial energy. So if we write it, it's the change of energy is equal to change in internal energy, plus change in kinetic energy plus also the change in potential energy. For a closed system with positive work and heat transfer, the the heat transfer minus the work is equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy. So what is the main importance of the first law of thermodynamics? The first law of thermodynamics is significant because it explains the relationship between heat transfer, work performed, and the changes in a system internal energy. So there are four main points. First one is the conservation of energy. It explains how energy is conserved in various processes. The second point is interdependence. This shows how energy and work are interdependent in a system. Quantification allows for precise calculation for energy transfer and also understanding of our process. This first law provides us with a framework for understanding the natural and engineered process. Now we will be taking a look at the second law of thermodynamics. The second law of thermodynamics addresses the direction of thermodynamic processes and also introduces the concept that energy has both quality and also quantity. So there's three main points that we need to learn from second law is the process direction. Second law of thermodynamics determines whether a process can occur spontaneously, and also it introduces the concept of entropy as an unconserved property. And finally, it also establishes theoretical limits for engineering system, which from knowing the efficiency limits. So one of the main thing we need to know for the second law of thermodynamics is the Kelvin-Planck statement. The Kelvin-Planck statement of the second law of thermodynamics asserts that no device operating on a cycle can accept heat from a single reservoir or produce a net amount of work. So for example, for heat engine, this requires both high and low temperature reservoir. For efficiency limit, no heat engine can have 100% thermal efficiency, and for our power plants, must exchange heat with boiler and also the environment. Another one is closure statement. The closure statement asserts that it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. So for example, refrigerators and heat pumps require work input to transfer heat from cold to hot or hot to cold. So the Kelvin-Planck and the closure statement are equivalent expressions of the second law of thermodynamics. A violation of one implies a violation of the others. So a combined heat engine and refrigerator is a device violating the Kelvin-Planck statement which means that this also violates the closure statement when combined with a refrigerator. So the Carnot cycle, proposed by French engineer Sadi Carnot in 1822, is one of the most well-known reversible cycles in thermodynamics. It consists of four reversible processes. First one is reversible isothermal expansion, where heat absorbed from high-temperature reservoir. Second one is the reversible adiabatic expansion. Temperature decreased from TH to TL, as you can see from the diagram there. Third one is reversible isothermal compression. Heat rejected to lower temperature reservoir. And the fourth one is reversible adiabatic compression, where temperature increases from TL to TH. And then one thing that we need to know in a heat transfer process is the thermal efficiency. Thermal efficiency is a measure of how well a heat engine converts heat input into output. So to calculate that, we have a formula. Thermal efficiency equals to work divided by heat input. So another thing that we must know is entropy. So entropy is a property introduced by the second law of thermodynamics. It can be thought as a measure of molecular disorder or randomness. So for a definition, it's a measure of a system thermal energy per unit temperature that is unavailable for doing useful work. So for entropy change is the delta S equals to S2 minus S1. For an entropy generation, the entropy generated must always be positive or zero. For isolated system, the entropy must always be zero, always increases or remains constant. So we need to know entropy and irreversibility. Entropy generation is a measure of the irreversibility present during a process. It can be used as a quantifiable measure of a process irreversibility. So for a reversible process, the entropy generated is equal to zero. For an irreversible process, entropy generation must be more than zero. The degree of irreversibility, the higher the entropy generated indicates the more the irreversibility. One of the things that we need to know for second law is isentropic process. An isentropic process is one in which the entropy remains constant. It is typically a reversible adiabatic process. So the definition here is entropy, change of entropy, S is equal to 0, where S2 is equal to S1, as we can see from the diagram. So in application, it is used in analyzing pumps, turbine, nozzles, and diffusers. In ideal condition, this is used to compare real performance to ideal conditions. So what are the importance of the second law? The second law of thermodynamics has significant implications and applications. There are four main purposes. The first one is to determine the degrees of spontaneity in a process or reaction. The second one, we can also use second law to determine and estimate the Earth's age, used in method to estimate the age of the Earth. And third one is energy efficiency. This guides the development of more energy efficient technologies by using the applications of the second law. The fourth one is natural processes. This explains the direction and limitations of natural processes. So to conclude things out, thermodynamics focuses on the behavior of heat and temperature and their relation to energy and work. The laws of thermodynamics provides fundamental principles for understanding and analyzing energy systems. So there is four main things that we have learned today. First is first law, which is energy conservation and transformation. Second one is second law, which is the process direction and efficiency limit. Apart from that, we have also learned the applications of these two laws in engineering, natural sciences, and also the technology development. Fourth thing we have learned today is the importance of these two laws. It is crucial to use these two laws to develop energy efficient technologies and understanding the natural phenomena of the world. So here are the references that I've used in this video.